In our last lecture, we talked about infinite limits. That is, when a function is approaching a particular number c, and the function values themselves are going up, higher and higher. They're increasing without bound. We say that that limit is infinity. Or if the function is getting smaller and smaller, we say that that limit is negative infinity. We determined also from that we could look at an algebraic expression that is the function, and anywhere the denominator equals 0, then that's where we have a candidate for an asymptote, which is the same thing as a limit being infinity or negative infinity. Those were vertical asymptotes. Well, today we're going to talk about horizontal asymptotes, and horizontal asymptotes we determine by looking at what's happening as the x value is going to infinity or to negative infinity. So let's talk about what we mean by that. If we've got a function, we're saying as it goes out in this direction, as x gets larger and larger and larger, that's what we're trying to determine today, is what is happening there, and that those will be candidates for horizontal asymptotes. The basic rule that you need to be sure that you remember from this is right here. The limit as x approaches infinity of any constant number over x to some power equals 0. And let's think about why that's true here. If you think about trying to evaluate this function right here numerically, if we put numbers in for x, larger and larger numbers, and we raise them to a power, even x to the first or x to the second or x to the third, any positive power, this number on the bottom is getting larger and larger. Well, the numerator is staying the same, so we're taking a number and dividing it by a different number that's getting larger and larger and larger. As that number gets larger and larger and larger, the entire fraction is getting smaller and approaching the number 0. So as we're trying, anytime that we're asked to evaluate a limit as x approaches infinity, we want to get our equation, get our algebraic expression looking like this if at all possible, because it'll make it easier to evaluate then. So let's look at an example. So when we look at this problem here, we've got a number minus another number. So let's first of all break it up into two different algebraic expressions. We can say it's the limit as x approaches infinity of -3 minus the limit as x approaches infinity of 2 over x to the 4th. Well, this is just a constant number. It's not going to change no matter what we put in. So this limit is going to be -3 minus the limit as x approaches infinity of 2 over x to the 4th. That fits our rule that we looked at on the previous slide. That limit is going to be 0. So this function, -3 minus 0, if we look at this and do the algebra, we get -3. So we can say that this function here, as x gets larger and larger, is approaching the number -3. So what does that tell us about trying to graph this? If we are looking at this function, we know that as it gets further and further out here, the function is going to be getting closer and closer to the number -3. So we know that the function's either going like this, in which case we have a horizontal asymptote at x equals -3, or the function is going like this and coming up from below. But one of these cases has to be true. It's either looking like this or this. So it gives us some idea of what the function is doing. And as we go through and learn more about calculus, we'll have more scenarios where we know things about what's happening with the function at particular places. So as x approaches as x approaches infinity, the function is approaching -3 in this case. Well, let's look at this problem. As x approaches infinity, what's happening to this expression here? Well, if we look at it, a way to solve this would be algebraically or one way you may consider is plugging in. Well, we don't have a number to plug in up here, do we? But we do have, we can plug in numbers and try to evaluate it numerically. So why don't we do that? What if we say 2 times 1,000 minus 1 over 1,000 plus 1? So that's going to give us 1,999 over 1,001. And if you do that on your calculator and divide it out, you're going to get a number a little bit smaller than 2. It's going to be around 2, though. You should try that on your calculator and verify that I'm correct there. Let's try a number even larger. What if we say 100,000? 2 times 100,000 minus 1 over 100,000 plus 1. That will give us 199,999 over 100,001. Again, which is giving us approximately a value of 2. And you can do that for several scenarios and look at it, and you'll see as the numbers get larger and larger, the limit continuously goes closer and closer to the number 2. Now, if you're using your calculator, you'll get to a point where it looks like it is the number 2, but it will never be exactly 2. Your calculator is just limited in what it can actually show on the screen, but it will be approaching the number 2. Well, let's look at these 3 examples here, which, if you look at them, they're very similar to one another in format here. They all have the same coefficients. They all have the same denominator. The only thing that's different is the 5x, 5x squared, and 5x cubed. So I'm going to ask you now to stop the video for a moment, try and evaluate each of these by the same method that we just did on the previous problem. That is, plugging in numbers larger and larger and see what you get out, see what it appears that you get out each time. Well, as you've gone through and done the problems, you should have found that this limit is approaching the number 0, and that this limit is approaching the number 5 over 7, and that this limit is approaching, continuously gets larger and larger, and that this limit is approaching infinity. Those are the 3 answers you should have gotten out simply by plugging in numbers. I would plug in 1,000 or 10,000 or 100,000, whatever the case might be there. As an example, let's pull up our calculator and let's try one of these particular problems here. As you see here, I've got the last limit typed into my calculator, and we're going to look at a table set of that calculator, and we're going to start at 1,000 and go up by 1,000 because we really want to see what's happening as x gets larger and larger. So as we do that, we see that it's 714, 1428, and it's continuously getting larger and larger the number as we go on up. So if we go to 9,000, it doesn't seem to be getting to a place that is stopping. And you can go up as far as you might want here, and you'll see that it continuously goes up higher and higher. So that's the process I would use to solve these other 2 as well, and you should come up with the results that I have here. The main thing I want you to see with all of this is, what can you determine by looking at this? Look at the problems, look at the solutions, and what generalizations can you make? What can you conclude from it? Is there a way to look at this problem and know that the answer is going to be 0? Is there a way to look at this one and know that it's 5/7, or look at this one and know that it's infinity? And the answer to that is yes. If you look in this first problem, we have the highest exponent is in the denominator. So if we look in the denominator and we see an exponent that's higher than this one up here, the largest exponent is in the denominator, the limit is always going to be going to 0. If we look and we have the same exponent in numerator and denominator, meaning the highest exponent in the numerator is the same as the highest exponent in the denominator, then the limit's going to be that number, that lead coefficient, over that lead coefficient, 5 over 7. And if the highest exponent is in the numerator, then that function is going to be going to infinity. And these are rules that you should have learned in previous classes, and here they are just summarized. Anytime you're looking at limits going to infinity or negative infinity, these are the three rules that you can use. If the degree of the numerator is smaller, the limit is 0, and there's a horizontal asymptote at y equals 0. If the degree is the same in both, then the limit is a over b, where that's the lead coefficient over the lead coefficient. And that also means there's a horizontal asymptote there. And if the degree in the numerator is larger, then the limit is either infinity or negative infinity, and there's no horizontal asymptote. So those are three rules that you need to memorize as we move forward in solving these problems. Well, let's look at this problem. The limit as x approaches infinity of cosine x. Let's start off by looking at a graph of this.